In materials that exhibit antiferromagnetism, the magnetic moments of atoms or molecules, usually related to the spins of electrons, align in a regular pattern with neighboring spins on different sublattices, pointing in opposite directions. This is, like ferromagnetism and ferromagnetism, a manifestation of ordered magnetism. The phenomenon of antiferromagnetism was first introduced by Lev Landau in 1933. Generally, antiferromagnetic order may exist at sufficiently low temperatures, but vanishes at and above the Néel temperature, named after Louis Néel, who had first identified this type of magnetic ordering. Above the Néel temperature, the material is typically paramagnetic. Measurement when no external field is applied. The antiferromagnetic structure corresponds to a vanishing total magnetization. In an external magnetic field, a kind of ferromagnetic behavior may be displayed in the antiferromagnetic phase, with the absolute value of one of the sublattice magnetizations differing from that of the other sublattice, resulting in a non-zero net magnetization. Although the net magnetization should be zero at a temperature of absolute zero, the effect of spin canting often causes a small net magnetization to develop, as seen, for example, in hematite. The magnetic susceptibility of an antiferromagnetic material typically shows a maximum at the Néel temperature. In contrast, at the transition between the ferromagnetic to the paramagnetic phases, the susceptibility will diverge. In the antiferromagnetic case, a divergence is observed in the staggered susceptibility. Various microscopic interactions between the magnetic moments or spins may lead to antiferromagnetic structures. In the simplest case, one may consider an Ising model on a bipartite lattice, e.g. the simple cubic lattice, with couplings between spins at nearest neighbor sites. Depending on the sign of that interaction, ferromagnetic or antiferromagnetic order will result. Geometrical frustration or competing ferro and antiferromagnetic interactions may lead to different and, perhaps, more complicated magnetic structures. The relationship between magnetization and the magnetizing field is nonlinear, like in ferromagnetic materials. This fact is due to the contribution of the hysteresis loop, which for ferromagnetic materials involves a residual magnetization. Antiferromagnetic materials' antiferromagnetic structures were first shown through neutron diffraction of transition metal oxides such as nickel, iron, and manganese oxides. The experiments, performed by Clifford Shull, gave the first results showing that magnetic dipoles could be oriented in an antiferromagnetic structure. Antiferromagnetic materials occur commonly among transition metal compounds, especially oxides. Examples include hematite, metals such as chromium, alloys such as iron manganese, Fe(Mn), and oxides such as nickel oxide, Neo. There are also numerous examples among high nuclearity metal clusters. Organic molecules can also exhibit antiferromagnetic coupling under rare circumstances, as seen in radicals such as 5-dihydroxyzylylene. Antiferromagnets can couple to ferromagnets, for instance, through a mechanism known as exchange bias, in which the ferromagnetic film is either grown upon the antiferromagnet or annealed in an aligning magnetic field, causing the surface atoms of the ferromagnet to align with the surface atoms of the antiferromagnet. This provides the ability to pin the orientation of a ferromagnetic film, which provides one of the main uses in so-called spin valves, which are the basis of magnetic sensors, including modern hard disk drive redheads. The temperature at or above which an antiferromagnetic layer loses its ability to pin the magnetization direction of an adjacent ferromagnetic layer is called the blocking temperature of that layer, and is usually lower than the Néel temperature. Geometric frustration, unlike ferromagnetism, antiferromagnetic interactions can lead to multiple optimal states, ground states, states of minimal energy. In one dimension, the antiferromagnetic ground state is an alternating series of spins, up, down, etc. Yet in two dimensions, multiple ground states can occur. Consider an equilateral triangle with 3 spins, one on each vertex. If each spin can take on only 2 values, up or down, there are 23 is equal to 8 possible states of the system, 6 of which are ground states. The 2 situations which are not ground states are when all 3 spins are up or are all down. In any of the other 6 states, there will be 2 favorable interactions and 1 unfavorable one. This illustrates frustration, the inability of the system to find a single ground state. This type of magnetic behavior has been found in minerals that have a crystal stacking structure, such as a cagome lattice or hexagonal lattice. Other properties, synthetic antiferromagnets, often abbreviated by SAF, are artificial antiferromagnets consisting of 2 or more thin ferromagnetic layers separated by a non-magnetic layer. Dipole coupling of the ferromagnetic layers results in antiparallel alignment of the magnetization of the ferromagnets. Antiferromagnetism plays a crucial role in devices employing giant magnetoresistance, GMR, an effect discovered in 1988 by the Nobel Prize winners Albert Fert and Peter Grunberg, awarded in 2007. First, for antiferromagnets being employed as pinning layers, and also since the original device design. Iron-chromium-iron multilayer with a CR layer thickness carefully tuned amounts to a synthetic antiferromagnet. There are also examples of disordered materials, such as iron phosphate glasses, that become antiferromagnetic below their Néel temperature. These disordered networks frustrate the antiparallelism of adjacent spins. It is not possible to construct a network where each spin is surrounded by opposite neighbor spins. It can only be determined that the average correlation of neighbor spins is antiferromagnetic. This type of magnetism is sometimes called speromagnetism, exchange bias giant magnetoresistance, phenomenon involving the change of conductivity in metallic layers geometrically frustrated magnet. Complex structures in matter physics pages displaying short descriptions of redirect targets, Ising model. Mathematical model of ferromagnetism in statistical mechanics, ANNI model. Variant of the Ising model Mottness. Materials classically predicted to be conductors that are actually insulators pages displaying short descriptions of redirect targets. Quantum spin liquid, phase of matter ferromagnetism. Mechanism by which materials form into and are attracted to magnets, diamagnetism. Magnetic property of ordinary materials.